Thank you for the introduction. And indeed, today I will show you how to represent complex policies on existing network infrastructure, which is a joint work of me and my supervisors, Kirill Kogan and Sergey Nikolenko. Modern networks must implement a wide range of services. And the growing complexity and the number of these services raises resource demands for individual network elements. And in particular kind of resource that will be our interest today is the TK memory, which is a state-of-the-art solution for representing packet classifiers. So faced with the growing demand for TK memory, we could try to just buy new infrastructure, more powerful with more memory, but obviously this is expensive, and instead we better find some efficient and scalable solution that would allow us to reuse and better exploit the infrastructure that we have. And one approach that leads to such a solution was initially proposed at Infocom 2013 and then improved at Connect the same year. And the basic idea was to make the placement of the classification policy more flexible in the following way. So consider some classification policy here. In this policy, we identify some flow-specific parts, and we assume that to each flow there corresponds some path in the network. And now we are free to take these flow-specific parts and split them along the path in a more or less arbitrary way. As soon as we maintain the equivalence with the initial policy and we feed the switch capacity. So this gives us more flexibility. And the important building block here is this operation of taking the flow-specific policy, switch capacities along the path, and finding this equivalent splitting. To formally define the problem, I need a notion of a classifier, which is quite simple. It's just a prioritized set of rules where each rule consists of a pair of a term and a bit string, a filter that represents a matching pattern, and an action. What we want from our classifier is we want to perform a lookup on it, which is simply finding the highest priority rule that matches the given header. So here is just an example of a classifier with 4 rules. The classification width is 4. Here we have actions. Here we have a filter for each bit in the header. And the rules are prioritized from top to bottom. What we want to find is we want to find a splitting of a classifier, which is a sequence of classifiers that is equivalent to the given classifier. Equivalent in the sense that it must apply the same actions to any given header. Here on the left, we have, on the right, we have an example of a splitting of this classifier. And splitting operates basically as follows. It takes a header, matches in the first classifier, applies actions immediately, this is important, then goes to the next classifier, and so on. For example, if we take this header, then it will not be matched in the first part of the splitting. It will be matched somewhere here. And this is the same result as we will get here. And here, this header is a more interesting example because it matches in both parts of the splitting. But it matches here, and it also matches here. But here we will have a special no-op rule, no-op action that will do nothing to maintain equivalency. It will show to be useful in the future. And so our problem is the following. Given a classifier and switch capacities along the path, we want to find such a splitting that each element of the splitting has no more rules than the capacity of the corresponding switch. So what we want from our solution? We want it to be as feasible as possible, meaning that it must find valid splittings for as many different combinations of capacities as possible. It must be correct, so it must be equivalent, which, as we will see next, is not always the case with the existing solutions. And it should be efficient both in terms of the running time and in terms of the total classifier memory that it uses. And I start with the solutions that do not use any metadata. And one such solution is a palette that was suggested at Infocom 2013. And basic idea is the following. We take classifier, select some column in it, then all don't care these bits are expanded. They are replaced with 0 and 1 replicating rules. And then all the rules that have 1 in that column are moved to the first component. And all other rules that have 0 go to another component of the splitting. This approach is very simple, but it has a number of disadvantages. First, rules are duplicated, There is no candle for heterogeneous capacities, and header space is always cut in half, which may be suboptimal, especially if we have a path length that is not the power of 2. So the OBS that was suggested at Connect, it tries to improve, it actually improve over the palette. It solves some of these problems, and the basic idea here is to proceed not like iteratively, this step is performed in some greedy fashion until we get the solution. But here we proceed incrementally. That is, we first try to feed some of the rules to the first classifier, then some of the rest of the rules to the second, and so on. And basically, at each step, we select not half of the header space. We select some rectangle that does not intersect with more rules that we can fit into the current switch. Then we put into the switch all the rules that are in this rectangle, while restricting these rules into this rectangle. So basically, we just what we do next, before we go to the next switches, we remove from our current classifier all the rules that were completely covered already by this switch. And additionally, we add a special rule, no op, for this rectangle that avoids matching in this rectangle repeatedly, like in the subsequent classifiers. But this solution still, it causes rule duplication, and it's not clear how to efficiently scale this solution to more fields. So it requires a rectangle, and if we increase the number of dimensions, the performance degrades. And the rules that we put in the switch must correspond to a rectangle, which is a limitation. So our first contribution here is a Boolean minimization application to this problem. That tries to kind of generalize this OBS approach. What we do is that we proceed in the same incremental fashion as OBS, but at each step, we take this current classifier and we split these rules among the current switch and the subsequent switches in the path in arbitrary fashion. So we do not require these rules to somehow fit in the rectangle. But then to maintain the equivalency, we in each part, we replace all the rules that we have deleted with no op actions. We replace the actions with no op. And then, which is important, we run Boolean minimization, any kind of Boolean minimization heuristic that we have to decrease this added part of no op rules. So for example, here we can just fold these 3 rules into the one. And this approach still duplicates rules, as we see, and it has its own problems that are related to the switch that has a catch-all rule. This switch may require a lot of knob rules that cannot be reduced by Boolean minimization. So to summarize, if we use some technique that does not use metadata, they all have the same disadvantages. Either for example, they cause rule duplication for different reasons. They have relatively slow running time. And what is more important, that they show incorrect behavior if we have dynamic fields. By dynamic fields, I mean those parts of the header that are changed, that can be both changed by an action and participate in classification. For example, here we have an example. We have a solution produced by Palette that is supposedly equivalent, but here we add actions that actually change the bits that participate in the classification. And if we follow with this header matchings in both in sequence, so we match here, we change the first bit, and surprisingly, we again match in this classifier that we shouldn't be matching this rule. In the original classifier, we would only match in this rule, and the output of the classification would be the header consisting of all zeros. But here we have a repeated matching because of these dynamic fields. The main idea is to use metadata, and surprisingly, just one bit of metadata can solve all of the problems that we had before. To understand how it works, just consider why the naive solution to the problem fails. So the naive solution is we have a classifier, we have 2 switches, both having 2 rules, capacity 2, and we just take first 2 rules, put in the first switch, the next 2 rules, put in the second switch, and that's it. But it doesn't work. It's not correct because some of the headers, for example, this one, it can be matched twice. So the idea is simply not to let that header to match twice by using a matched bit that is set every time that when header is matched. And in the subsequent switches, we always, before classifying the packet, we first check if this bit is set. If it's not set, then we classify. If it's already set, we simply do not classify. And this simple solution leads to an algorithm which is called 1-bit, and which has a very simple feasibility condition. So it's just the total capacity must be at least the number of rows in the initial classifier. It has linear running time, and it essentially does not produce any new rules. So the total number of rules is trivially the same number of rules that we had. It's a very simple solution using just 1 bit of metadata. Moreover, this solution allows us to improve the network-wide solution that was a part of OBS work. And that solution initially proceeded as follows. First, it tried to find some estimation for total required capacity for each flow. Then it used that estimation and linear programming to allocate capacities for individual flows. And finally, it tried to solve the flow split for each flow. But it could fail. And if it failed, it went back to the first step. With 1 bit, we don't need all this complexity. We don't need any estimates. We simply take the number of rules in the classifier corresponding to a flow as our estimate, and then we just solve this problem because theorem guarantees that we are able to solve it. And finally, to summarize, just 1 bit of metadata allows us to trivialize the solution to flow split problem. This solution is correct, it's trivially efficient, and it's correct even with dynamic fields, and it facilitates the fast network-wide solution. Thank you, and I'll be glad to answer some questions if we have time.
Let's thank our speaker.